Hello, this is Matt Dean with A Plus College Ready, and today we're going to talk about waves. First of all, we'll start with just some terminology that you need to be familiar with. A wave is a disturbance in a medium that transmits energy without transmitting matter. We'll talk about some different types of waves. Mechanical waves are waves like the wave that might go through a rope or a sound wave, waves that require a medium, something to vibrate, to move. There are also electromagnetic waves. These don't require a medium. They're essentially vibrations of electric and magnetic fields. They can travel through space at very high speeds. These are like the different forms of light. Let's also talk about transverse and longitudinal waves. A transverse wave is a wave in which the vibration of the medium is perpendicular to the actual movement of the energy or the velocity of a wave. Think of a transverse wave like a wave on a string. A longitudinal wave, on the other hand, is a wave in which the vibration of the medium is parallel to the direction of the motion of the wave. This is like a sound wave. This kind of wave is made up of alternating compressions and rarefactions or expansions. So let's look at that on some pictures. So here's a longitudinal wave in a slinky. So in this case, we compress the slinky, and then it's going to rarefy, compress, rarefy, and so on and so forth. Well, here we can see it with sound, that it's alternating compressions and then rarefactions, where the particles expand away from each other. So the distance between any two of these compression bands would be a wavelength. A transverse wave, on the other hand, is like if you took a slinky, attached at one end, and you started moving it up and down. So the actual slinky is vibrating this way, but the energy and the movement of the wave is actually this way. They're perpendicular to each other. So the vibrations of the particle and the actual movement of the energy are perpendicular to each other in transverse waves. So again, just a couple more pictures. Remember, sound is a type of pressure wave. It's a longitudinal wave. It's composed of alternating compressions of the particles and expansions of the particles, or rarefactions. And this diagram is showing us that we can find the wavelength essentially by going from the center of a compression to the center of the next compression. We could also go from the center of a rarefaction to the center of the next one. That would also be a wavelength. This length should be the same as this length. Let's also talk about some basic properties of waves. The period is the time required for one complete cycle or one complete wave to take place. We often will see it abbreviated with capital T, and it's typically going to be measured in seconds. The frequency is the number of waves that occur per unit of time, usually per second. Frequency is oftentimes it's inverse of the period. So the period is 1 over the frequency, or the frequency is 1 over the period. We usually measure frequency in hertz, or cycles per second, waves per second in this case. The wavelength we symbolize with the letter lambda. It's the distance between two successive crests or two successive troughs on a wave. It's measured in the direction of the wave. It's usually measured in meters or some kind of relation of meters, like centimeters or something. It can be measured from the same 2 points on any adjacent waves. We'll also talk a lot about the wave equation. The wave equation is about the speed of a wave. So V is the speed of the wave, and that's equal to the wavelength times the frequency. So if you have a wave occurring in a particular medium and you increase the frequency, well, then the wavelength has to decrease, assuming the speed has to stay the same. So the speed of a wave is not determined by the wavelength or the frequency. The speed is determined by the medium. Things like the tension in the rope or the elasticity of the particles in a solid. So we're not saying that wavelength and frequency determine the speed. We're saying they're properties of the speed. The medium, the properties of the medium determine the speed of the waves that travel through it. The crest is the point on a medium that exhibits the maximum amount of positive or upward displacement from the rest position, and a trough is the point on the medium that exhibits the maximum amount of negative or downward displacement. And the amplitude is the amount of displacement away from the equilibrium position. So for example, if we had an equilibrium line going through the middle here, let's try that again. Where's my pen not working? Well, that's terrible. Let's try that again. Let's say this is equilibrium. So if that's equilibrium, the amplitude could be the maximum upward displacement. It could just as easily be the maximum downward displacement. These would all be crests, and these would all be troughs. Notice that this wave has more waves per second, so it has a higher frequency. This one has a lower frequency, and this one has even a lower frequency. This equation is not found on your AP formula sheet. It's one that I would go ahead and memorize, though. It's for the speed of a wave, particularly the speed of a wave in like a rope or string. And it's telling you essentially that the speed of the wave is equal to the square root of, this is the tension force in the rope, divided by the mass of the rope, divided by the length of the rope. And then let's take the square root of that whole quantity. So again, remember, the speed of a wave is determined by the properties of the medium. In this case, the tension force in the rope, the mass of the rope, and the length of the rope. Sometimes that M over L quantity, you'll hear it called the linear mass density, and you'll see it abbreviated with the letter mu. Let's look at a couple of sample wave problems. All right, so first practice problem. A traveling wave on a rope has a frequency of 2.5 hertz. If the speed of the wave is 1.5 meters per second, what are its period and its wavelength? So a traveling wave is a wave that appears to move up and down the medium, in this case, up and down the rope. First of all, we know the frequency, and we know that the period is equal to 1 over the frequency. So our period is going to be 1 over 2.5 hertz. So let's go 1 divided by 2.5, and we end up with a period of 0.4 seconds. Now to find the wavelength, we're going to use the wave equation, which is speed equals wavelength times frequency, which means wavelength equals speed divided by frequency. So let's take the speed, 1.5 meters per second, and let's divide that by the frequency, this frequency, which is 0.40 seconds. So 1.5 divided by 0.4, and we end up with a wavelength of 3.75 meters. So with two sig figs, we'll say 3.8 meters for our wavelength. All right, problem 2 is a similar kind of problem. The period of a traveling wave is 0.5 seconds. Its amplitude is 10 centimeters, and its wavelength is 0.4 meters. What are its frequency and its wave speed? All right, so remember, frequency is 1 over the period. So we know the period. The period is 0.5 seconds, so 1 divided by 0.5, and we get 2 for the frequency. So the frequency is going to be 2 hertz. And to find the wave speed, we'll use that wave equation. Wavelength, or speed equals wavelength times frequency. Our wavelength is 0.4 meters. Our frequency, 2 hertz. So we end up with a wave speed of 0.8 meters per second. Now notice that we didn't need the amplitude data that was given to us in that problem. Very oftentimes you'll be given extra information that you don't need. You have to be able to sort that out. Moving on down to number 3. A horizontal rope with a linear mass density of mu sustains a tension of 60 newtons. The knot attached end is oscillated vertically with a frequency of 4 hertz. What are the speed and wavelength of the resulting wave? All right, so first of all, the speed of a wave is equal to the square root of the tension force over the linear mass density, which in this case would be 60 newtons divided by 0.5 kilograms per meter. We can't forget to take the square root of that whole quantity. So 60 divided by 0.5, take the square root of that quantity. We end up with a speed of about, let's see, we need really just 1 sig fig. So we'll just round it off to 11 meters per second here is our speed. Now we're also looking for the wavelength. So remember that speed equals wavelength times frequency. Wavelength equals speed divided by frequency. So let's take our speed, 11 meters per second, divided by our frequency of 4, and that's 4 hertz. So 11 divided by 4, we end up with a wavelength of, we'll say 2.8 meters on this one. Now, last part, how would you answer these questions if F were increased to 5 hertz? Well, let's assume the tension stays the same. That means the speed can't change. So if the frequency goes up, the wavelength must go down. So we would just simply change this 4 right here to 5. And we would go 11 divided by 5. And we would end up with a new wavelength of about, instead of 2.8, we would end up with a new wavelength of about 2.2 meters. All right, so some other properties of waves. One of them is reflection. That's when a wave bounces off of a barrier. And there's an important law, it's called the law of reflection. And it says that the angle of incidence, so let's say this is the incident ray is our incoming wave. It hits a reflecting surface. Essentially, it says that the angle of incidence is equal to the angle of reflection. Now, that angle is measured from a normal line, a line that's perpendicular to the reflecting surface. And the angle is the angle between the incident ray and the normal. So we're saying that that angle, the angle of incidence, has to be equal to the angle of reflection. Again, that angle is also measured from the normal to the reflected ray. So we're saying that these two angles, the angle of incidence, has to equal the angle of reflection. That's called the law of reflection. We can also talk about refraction. Refraction is when a wave bends because the medium changes. For example, water waves moving from deep to shallow water will bend their paths, they'll slow down, and they'll shorten their wavelength. The frequency doesn't change. You've seen that if you stick something underwater that looks like it's bent, that's because of a refraction, a change in the medium. There's also diffraction. This is when waves bend around a barrier. For example, water waves bend around a rock in a stream. Water waves, when they pass through can pass through a narrow slit. We won't talk a lot about diffraction in this course. It'll be more important when we get to optics. Let's talk about superposition and the principle of superposition. When two waves interfere, the resulting displacement of the medium at any location is the algebraic sum of the displacements of the individual waves at that same location. Superposition essentially means two waves end up on top of each other. And here we're saying that essentially their amplitudes have to add together. Wave interference is the phenomenon that occurs when two waves meet when they're traveling along the same medium. That interference causes the medium to take on a shape that results from the net effect of both waves, the sum of the two waves. Interference occurs when two waves travel through the same medium and they meet at a certain point in time. We can have constructive interference. This is when if the waves are moving over the same point, they're in phase, and the waves actually build on each other. A crest meets a crest. So the resulting crest is taller than that of either individual wave. We can sometimes call that an antinode, a point of maximum displacement. We can also get destructive interference. And this is two waves that are of equal magnitude moving in opposite directions, and they're out of phase. So let's say a crest meets a trough. If they're of equal amplitude, the crest and the trough will cancel each other out, and we'll get a point of no displacement, which we sometimes call a node. So here we can see waves A and B. They meet in the middle, and since they were in phase, we got constructive interference. So this is constructive. On the other hand, here they're out of phase, and somewhere in here, this crest is going to meet this trough, and when they do, they cancel each other out. That's destructive interference. Here we see two very different waves, but these two very different waves can add together. For example, right in here, crest and crest get together. So notice you get a little taller. On the other hand, maybe say in here, trough and trough meet. So it goes further down. The amplitude goes further in the negative direction. Here we have two waves of very similar frequencies. And when they interfere, we're going to get what are called beat patterns. And that's what we see in green. These beat patterns are essentially alternating patterns of constructive interference when crest meets crest or trough meets trough. And then we also get quiet points or nodes where crest meets trough. So they're alternating patterns of constructive and destructive interference. And if you see this pattern, you need to realize it's a beat pattern. If these were sound waves, you could hear the sound get louder, quieter, louder, quieter, louder, quieter. All right, we also want to talk a little bit about standing waves. Standing waves are patterns produced in a medium when two waves of identical frequencies interfere in such a manner to produce points along the medium that always appear to be standing still. So these are sort of the opposite of a traveling wave. You don't see a wave moving up and down the rope, but you see these points where there seems to be maximum amplitude and these points where the medium doesn't appear to move at all. The nodes are the points that appear to have no displacement. So at those points, you get complete destructive interference. Nodes form where a crest of one wave meets a trough of another wave. Antinodes, on the other hand, are the points along the medium that undergo large positive or large negative displacements and large negative displacements. These are the points of maximum displacement. Antinodes form because of constructive interference. They're where crest meets crest or trough meets trough. So here we see an antinode, antinode, antinode. The green dots, on the other hand, those are nodes. A standing wave is not actually a wave, but it's really a pattern. It's a pattern that results from the interference of two or more waves. An antinode is not really a point on a wave. It's a point on the wave pattern. A standing wave pattern always consists of alternating node and antinode. So standing wave patterns are produced within a medium when it's vibrated at a very certain frequency. Each frequency is associated with a different standing wave pattern. These frequencies and their patterns are sometimes called harmonics. And there's a very clear mathematical relationship between the wavelength of the wave that produces the pattern and the length of the medium in which that pattern is displayed, such as the length of the string. Each pattern corresponds to vibrations which occur at a particular frequency, again known as a harmonic. The lowest possible frequency at which a string can vibrate to form a standing wave is called the fundamental frequency, or we'll also sometimes hear it called the first harmonic. A complete wave in a pattern could be described as starting at the rest position rising to an upward peak displacement, returning back to a rest position, and then descending to a peak downward displacement, and finally returning back to the rest position. The animation that we see below sort of shows that. So a standing wave, one wave, let's let it play out here. So a complete wave is going to be what we call two loops, loop and loop. Each loop is 1/2 of a wavelength. So when we talk about loops, again, we're talking about one of these. And one complete wavelength is always going to be two loops in a standing wave. That'll be important for problems we'll work later. When we compare standing wave patterns for the first harmonic, we're going to see a single loop. So the first harmonic is going to look like one loop on the string or the rope. So what we'll be seeing with the first harmonic is 1/2 of a wavelength. So sometimes we'll use this equation, that the length of the string or the rope is equal to 1/2 the wavelength of the actual wave. Now that's for the first harmonic. Now if we vibrate the string with a frequency that establishes a standing wave for the second harmonic has 2 antinodes. So to determine the harmonic number, count the number of antinodes. Second harmonic has 2 antinodes. It also has 3 nodes. The third harmonic has 3 antinodes, 4 nodes. The second harmonic, on the other hand, is going to have 2 antinodes. Therefore, it's going to consist of 2 complete loops. So if we have a second harmonic wave on a string, that means that that string contains one whole wavelength, 2 whole loops. So in that condition, the length of the string is equal to the wavelength. So we might say the length of the string is 2/2 times the wavelength. So there's an equation that comes in handy. It essentially says that the length of the string is equal to n/2 times the wavelength, where n is the harmonic number. So for example, if we were talking about the fourth harmonic, L would equal 4/2 times the wavelength. So essentially, the length of the string would have to be 2 times the wavelength of the wave in order to get the second harmonic, the fourth harmonic rather. So to get standing waves, we must have a node at both ends of the string. A standing wave can only form, and this is important, standing wave can only form when the length of the string is a multiple of 1/2 the wavelength. We saw this equation earlier. L is equal to the harmonic number times 1/2 the wavelength. Here I simply solved that equation for lambda. Again, remember that n is the harmonic number. Here's our wave equation. We could do some fancy substituting between these two equations to derive this equation. Don't think you'll need that in this course. Remember that the first standing wave, the one that forms at the lowest frequency at which we can get a standing wave, is the first harmonic or the fundamental. And for that, n equals 1. So if we want to find the frequency of a different harmonic, we can say the frequency of, say, the second harmonic is equal to the harmonic number times the frequency of the fundamental. If we want to know the wavelength of a particular harmonic, the wavelength is equal to the wavelength of the fundamental divided by the harmonic number. So those equations might come in handy in some of the problems we'll see later. And actually, here are a couple of problems. So a string of length 12 meters that is fixed at both ends supports a standing wave with a total of 5 nodes. What is the harmonic number and the wavelength of the wave? All right, so this is a terrible drawing that I did up at the top of the page, but this has 5 nodes. 1, 2, 3, 4, 5. If a standing wave has 5 nodes, it's going to have 1, 2, 3, 4 antinodes. Remember that the number of antinodes is the same as the harmonic number. So in this case, we're looking at the fourth harmonic. And we also want to know the wavelength of the wave. Well, the string length is 12 meters. So from here to here is 12 meters. on that string, we have one complete wave there, 2 loops, and another complete wave there, 2 loops. So that 12 meters contains 2 complete waves. Therefore, the wavelength is 6 meters. All right, so let's look at problem 2. A string of length 8 meters is fixed at both ends and supports a standing wave with a total of 6 nodes. What is the harmonic number and the wavelength of this standing wave? All right, again, drawing appears terrible, but we have 1, 2, 3, 4, 5, 6 nodes. 1, 2, 3, 4, 5 antinodes. So that tells us in problem 2, we're looking at the 5th harmonic. The string is 8 meters long. It contains 1, 2, and 1/2 waves. So if we divide 8 by 2.5, 8 divided by 2.5, the wavelength here is going to be about 3.2 meters. All right, finally, let's look at example problem 3. A string of length 10 meters and a mass of 300 grams is fixed at both ends, and the tension in the string is 40 newtons. What is the frequency of the standing wave for which the distance between a node and the nearest antinode is 1 meter? First of all, we're going to need to find the speed of the wave in the string. So remember, speed is equal to the square root of the tension, 40 newtons, divided by the mass of the string. We're going to do that in kilograms, divided by the length of the string. So let's go 40 divided by 0.3 divided by 10. Let's take the square root of that whole quantity, and we end up with a speed of 3.65 meters per second. All right, so now we know the speed. We're trying to find the frequency. We need to use the wave equation. Remember that speed equals wavelength times frequency. We're going to solve that for frequency. So frequency is going to be speed divided by wavelength. Well, we know the speed is 3.65 meters per second. The wavelength, on the other hand, it says, what is the frequency of the standing wave for which the distance between a node and the nearest antinode is 1 meter? Well, the distance between a node and an antinode is 1/4 the wavelength. That distance is 1 meter. So the wavelength, therefore, is 4 times that. So our wavelength is going to be 4 meters. So let's go 3.65 divided by 4. And we're going to end up with a frequency here of 0.91 hertz. All right, let's move on a bit. So here we see a standing wave. Again, we've got a node, and another node, 3 nodes, an antinode, and an antinode. So this, remember, to determine the harmonic number, we count the number of antinodes. So this is the 2nd harmonic. The length of the string in this case is equal to the wavelength because this string supports 1 complete wave, 2 loops. Here we see some other harmonics. Here's the 1st harmonic. Remember, the 1st harmonic has 2 nodes and 1 antinode. The length of the string is 1/2 the wavelength of the wave. The 1st harmonic is the lowest frequency at which we'll get a standing wave. Here's the 2nd harmonic. 1, 2, 3 nodes, 1, 2 antinodes. The length of the string is equal to the wavelength. Here's the 3rd harmonic. 1, 2, 3, 4 nodes, 1, 2, 3 antinodes. And the length of the string is essentially 3/2 times the wavelength. Remember our general equation that the length of the string is equal to n, the harmonic number, times 1/2 times the wavelength. And remember that we'll only get a standing wave if the string is in a multiple of 1/2 the wavelength of the wave, the string length. So here's another practice problem. A standing wave is oscillating at 950 hertz on a string. what is the wave speed? We know to find the wave speed, wavelength times frequency. We know the frequency, 950 hertz. Well, in this diagram, the string length is 60 centimeters. Here's one complete wave, 2 loops. So, and then we got another half a wave. So what this tells me is that the wavelength is essentially 2/3 of the length of the string. So if we take 2/3 of 60, we're going to end up with 40 centimeters as our wavelength. We need to do that in terms of meters, so we're going to say 0.40 meters. So our speed is going to be our wavelength, 0.4, times our frequency, 950. And we're going to end up with a wave speed here of about 380 meters per second. Remember, this wave would be the third harmonic. It has 1, 2, 3 antinodes. All right, we can also set up standing waves in a pipe. And we're going to call them closed pipes because there's an end of a pipe, typically with some water in it, with some airspace up top. And we can set up a standing wave in that. Let me show you a picture. So let's assume that this is like where the water starts. And we could take maybe a tuning fork and put it right here and set up a standing wave. This is what we call the first harmonic. First harmonic, we have an antinode at the end of the tube. That means that this sound is going to get very loud right here. Here's the third harmonic. Again, we got an antinode here. Here's the fifth harmonic, an antinode. So when we're counting antinodes essentially. So if we send the waves down a pipe continuously at a rate that matches the rate at which they're reflected off the closed end, we'll get a standing wave. So again, it's caused by interference, positive and negative interference. If the length of the pipe is such that a whole number of quarter wavelengths fit into it, it's got to be quarter wavelengths so we can hear it. We'll hear loud tones called overtones or harmonics at approximately 1/4 the wavelength. When we hear those loud sounds, we're hearing the antinode. Now, if we go back to the picture, if there were a node here, we wouldn't hear anything, right? Because there would be no displacement, essentially. So if we know the frequency of the sound waves, like the type of tuning fork and the length of the pipe, we can use that to calculate the wavelength and the wave speed. For example, the speed of sound waves in air is 340 meters per second. Determine the fundamental frequency of a closed-end air column that has a length of 67.5 centimeters. All right, so go back to our picture here. This is what the first harmonic looks like. And remember that first harmonic, this is essentially 1/4 of a wave. It's 1/2 of a loop. Remember, a complete wave is 2 loops. So the length of the pipe, 67.5, that's essentially 1/4 the wavelength. So we need to go 67.5 and multiply that by 4. So the real wavelength is 270 centimeters or 2.70 meters. Now we're trying to find the frequency. So we know that speed equals wavelength times frequency. Frequency equals speed divided by wavelength. So let's take our speed, 340. Let's divide that by our wavelength in meters, 2.7 meters. So 340 divided by 2.7. We end up with a frequency of about 126 hertz on this one. All right, problem 2. Determine the length of a closed-end air column that produces a frequency, a fundamental frequency of 480 hertz. The speed of waves in air is 340 meters per second. So again, we're going to use the wave equation. Here we're looking for the length of the air column. So at first we're going to solve for the wavelength. So the wavelength is going to be equal to the speed divided by the frequency, which is going to be 340 meters per second divided by 480. And that's 480 hertz. So 340 divided by 480 340 divided by 480, we end up with a wavelength of about 0.708 meters. Now that's the wavelength of the whole wave. Remember that a fundamental is actually only 1/4 of a wave. So we need to take 0.708, divide that by 4, and we end up with the length of the air column, the answer to our question here, to be about 0.177 meters. All right, so we can also use this same idea to determine the speed of sound in a particular pipe. So let's look at number 3. Speed is equal to wavelength times frequency. So here we have a closed-in pipe of length 0.25 meters. It sounds out the first harmonic of a 349.2 hertz sound. We're looking for the speed of sound. So again, speed equals wavelength times frequency. Our frequency is 349.2 hertz. The wavelength. Now the length of the pipe is 0.25. The first harmonic, remember, there was only 1/4 of a wavelength, which means our wavelength is going to be 0.25 times 4, which ends up giving us a wavelength of 1 meter. So when we multiply 1 meter times 349.2, we end up with a speed of 349.2 meters per second. Now let's talk a bit about sound waves. Remember that sound waves are longitudinal waves. They're made of compressions of the medium, followed by rarefactions or expansions of the medium. Molecules of the medium move parallel to the direction of the wave propagation or the energy transfer. The speed of sound depends on properties of the medium, like the density and the bulk modulus, which is a measure of a medium's response to compression. Sounds generally travel fastest in solids, a little bit slower in liquids, and then slowest in gases. The speed of sound in air at 20 degrees Celsius is about 343 meters per second. The speed of sound in air increases with increasing temperature, according to this equation. So if the temperature was 0 degrees Celsius, the speed would be 331 meters per second. But for every degree up from 0 you go, the speed of sound increases by 0.6 meters per second per degree Celsius. So hotter means faster in terms of the speed of sound in air. That's important to know. So we've got a couple of sound waves problems here. A sound wave with a frequency of 300 hertz travels through the air at 20 degrees Celsius. What's its wavelength? All right, so to find its wavelength, we're first of all going to need to find its speed. And remember that speed equals 331 meters per second plus 0.6 times the temperature. And our temperature here is 20. So let's go 20 times 0.6 plus 331. So at 20 degrees Celsius, our speed is 343. Now we want to find the wavelength. To do that, we're going to use the wave equation. V equals lambda times F. Lambda equals V over F. So we're going to take our speed, 343 meters per second. We're going to divide that by our frequency of 300 hertz. So 343 divided by 300. For number 1, we're going to end up with a wavelength of about 11.4 meters. Number 2, if its frequency is increased to 600 hertz, what are the wave's speed and wavelength? Well, remember that the wave speed, that's determined by the temperature, by the medium. So the speed's not going to change. The speed is still 343. If, though, the frequency increases, this equation shows us that if this goes up and speed stays the same, then wavelength has to go down. So let's recalculate. Wavelength is going to be equal to speed, 343, divided by the new frequency, 600 hertz. So 343 divided by 600. We end up with a new wavelength of about 0.572. And that's 0.572 meters. Last one of these. A sound wave traveling through water has a frequency of 500 hertz and a wavelength of 3 meters. How fast does the sound travel through the water? So again, speed equals wavelength times frequency. So we've got the wavelength, 3 meters. We've got the frequency, 500 hertz. So we end up with a speed of 1,500 meters per second. All right, let's also talk a minute about beats. A beat is a phenomenon which occurs when two sound waves of different but similar frequencies approach the ear. We get these alternating patterns of constructive and destructive interference. And those patterns cause the sound to be loud, soft, loud, soft, loud, soft. And this is because the waves are moving in and out of phase. They're alternating between constructive and destructive interference. When constructive interference occurs, the sound gets loud. When destructive interference occurs, the sound gets soft. The formula for finding the frequency of the beats is essentially to take the frequency of one of the waves, subtract the frequency of the other waves. So for example, a computer simultaneously emits sounds of 450 hertz and 455 hertz. What's the beat frequency? To find that, we're just going to go 455 minus 450, and we'll get 5 beats per second. So every 5 seconds will alternate between loud and soft, loud and soft, loud and soft. Here's what a beat pattern will look like. So we have two waves of similar but different frequencies, and then they interfere with each other in alternating patterns, and these green wave patterns are the beat frequency, or the beat pattern rather. And again, they're made up of alternating constructive and destructive interference events. Finally, let's talk about the Doppler effect. When there's relative motion between the source of a sound and the detector, that could be an ear or some kind of sound detector, the waves that the detector receives are different in terms of both frequency and wavelength than those emitted from the source. If the two move toward each other, the detector perceives a higher frequency and a shorter wavelength. If the two move away from each other, the detector perceives a lower frequency and a longer wavelength. So we're talking about the perceived frequency. So there's an equation. This is the real frequency of the sound. This is the perceived frequency of the sound. Speed is the speed of sound through the medium. V sub 0 is the speed of the observer. And we're going to use the plus sign up here if the observer moves toward the source. We're going to use the minus sign if the observer moves away from the source. Down on the bottom of our fraction, Vs is the speed of the source relative to the medium. V again is the speed of sound through the medium. So we're going to use the minus sign if the source moves toward the observer, and we're going to use the plus sign if the source moves away from the observer. So this will let us calculate the perceived frequency of sound if either the source or the receptor, the receiver, are moving, or both. Maybe they both are. But the Doppler effect accounts for something like if you're standing still and an ambulance comes past you. As the ambulance approaches you, those sound waves get crunched together. And what you hear is a frequency that's higher than what the ambulance is actually creating. As the ambulance passes you, those wavefronts are moving further and further apart. So you actually hear a sound that is perceived to be lower in frequency than the actual sound that the ambulance is creating. And that's called the Doppler effect. All right, so here we have a source of 4,000 hertz sound waves traveling at 1/9 the speed of sound, let's just say at 20 degrees Celsius, toward a detector that's moving at 1/9 the speed of sound toward the source. What is the frequency of the waves as they are received by the detector? And how does the wavelength of the detected waves compare to the wavelength of the emitted waves? All right, so we're going to have to use this equation. Remember that f prime is the perceived frequency. So we're going to say f prime equals the actual frequency, 4,000 hertz, times the speed of sound through the medium, which we're going to say is 343 meters per second, plus or minus, on top of that fraction, the speed of the observer. The observer is moving toward the source, so we're going to use the positive sign, so plus. The observer is moving at 1/9 the speed of sound toward the source, so let's take 343 divided by 9, 38.1. All that's over the speed of sound, 343. We're going to use the minus because the source is also moving toward the observer. So also at 340 or 1/9 the speed of sound, so 38.1. So let's do the math. On top, 343 plus 38.1. That's 381.1 on top. On the bottom, 343 minus 38.1. That's 304.9 on the bottom. We've got to multiply that by 4,000. So 381.1 divided by 304.9. And we're going to multiply that times 4,000. We end up with a perceived frequency, our answer to part A, of 4,999.7. So the sound seems to be higher, it's perceived to be higher, because the detector and also the source of the sound are moving toward each other. So how does the wavelength of the detected waves compare to the wavelength of the emitted waves? Well, since the speed of sound didn't change and the frequency increased, that means the wavelength would decrease. So the wavelength would be lower than the when they're moving than when they're not moving. Here's another